All right, welcome back from the break. Today we are going to prove, this is CS4510, L06B. Today we're going to prove that every language which is decidable by a push-down automaton has a context-free grammar to do so. Now, two comments about this. First off, we are doing a real if and only if proof. And we've kind of skipped over a lot of them. We talked about regular grammars, and we're like, yeah, this is like, here's how you do the NFA, and then we did an example, and we're just kind of like, yeah. And we didn't really go into it, because computations are really intuitive things. So you can kind of look at it and be like, yeah, that obviously makes sense. We don't need to do a proof of that. Now this is one that doesn't make sense, because the construction is gonna be so complicated, you can't just take the PDA and then make the grammar and just be like, yeah, that grammar obviously is for the PDA. One, we could do the reverse really easy because we know how to write algorithms. We all know how to code. We take, making an automaton is like writing code. So it's the same kind of mental procedures we use to like take a, given a grammar and a word, how do we determine if that word is produced by the grammar? It's the same thing we do. So we know how to program a PDA. We don't know how to like intuitively, quote unquote, program a context-free grammar to simulate a PDA, right? How do you like program a context-free grammar? That's kind of what the difficulty in this proof is. And this is, I think, a very difficult proof. So let's have some patience on how hard this is, but note that we were supposed to do something of this caliber for basically every single simulation proof we did. We just kind of like hand waved it away, but we're gonna do one so you see how hard it is, so we have respect for why we don't do it that often. Okay. Now, before we begin, first off, PDA is ugly. They're horrible. There's all kinds of things with them. Let's do three. First, we're gonna make the PDA nice. And this is going to help with the grammar simulating the PDA, quote unquote. The grammar doesn't simulate anything. It just non-deterministically is a sequence of string writing rules. So like this, even saying simulate is kind of unintuitive. But we're gonna first make the PDA nice. First, it only has one except state. How can I make sure that my PDA only has one except state?
Epsilon transition from all except states to a new one.
This even works for NFAs, but if you have something like this, let's make it like this. Read nothing, pop nothing, push nothing. Read nothing, pop nothing, push nothing. Now, this PDA, after being modified, has one except state. Two, except only with an empty stack. There are two ways to do this one.
Is that what we did with the pop and the canary?
Yeah, so like one way you could do it is make sure that you have your read nothing, pop nothing, push the canary, and then you make sure you only accept when you pop the canary. That's one way to do it, right? And in fact, usefully, if you have stuff in the stack when you accept, you're not really using the stack to its full potential because you maybe didn't need to push those to begin with, right? So you can just kind of like manually program your PDA so that it only accepts with an empty stack. But if you had to modify the PDA, there's another way to do it. How do you make sure that PDA accepts with an empty stack?
You go to like a dump state that dumps everything out.
Yeah, instead of just like accepting, what you're gonna do is you're going to first dump, and then you're going to accept, right? So what that means, C and A or B in the stack, just throw it out. Let's be formal here. See nothing, pop, see nothing, pop, right? And then you accept. Three, each transition pushes or pops, but not both. How can I modify the PDA to ensure this property is true?
Any that does both, you break it up into two that have epsilons.
Precisely. So read an A, pop a B, push a C, let's say. This is equivalent to, if I read the A, and then I popped the B, and then later on, I take an epsilon transition, and then I push the C, right? Those are equivalent. So you could modify the PDA to have these three properties without changing the power. You've not restricted the power, you've not generalized the power. Any PDA can be made to have these three properties without changing the language. It decides. Agree? Okay. Now we need to talk about how does the computation actually proceed in a PDA, right? There are basically two cases. The first case is, we kind of have to look at the stack height, right? So the first case is that the stack is emptied at some intermediary step, right? Something like that, right? So let's say the stack is growing and pretend this is supposed to be like a discrete curve. I'm drawing it like in a, it could never be such a quadratic looking thing. It'll always be kind of like up, down, whatever, right? But suppose the stack is emptied at some intermediary point. Let's say you're at some state P at the beginning, and then you're at some state Q here, right, in the PDA, and you're emptied at some intermediary state R, right? So we want the PDA to, we want to somehow capture this in the transitions of our grammar. But how are we going to simulate these kinds of behaviors in our grammar? Basically what we're going to have is for all P comma Q, which are states, add non-terminal A, PQ. So we're going to add a pair of non-terminal. For every pair of states, we're adding a non-terminal, A, PQ. And we want that APQ will produce some string X, if and only if X brings the PDA from P with an empty stack to Q with an empty stack. So that's the first way we're going to simulate the, we're going to have these non-terminals to simulate pairs of states, and each non-terminal is going to produce a string that will bring the PDA from the start, from a state P to a state Q, right? Given this construction so far, forget this case for now. Given this construction, what should the start non-terminal of our grammar be? Yes?
The pair of the start state and every next state?
Ah, but we only have one.
We have one.
Except state.
Oh, so just one.
Yeah. So we would say that S is just a, let's say 0F for Q0 and QF, where QF is the accept state. Right? That's our singular accept state, right? So if A0F produces a string, that string takes the PDA from the start state with an empty stack to the final state with an empty stack. So the PDA accepts that string. So this non-terminal produces it. And again, we're trying to convert the PDA into a grammar. So this grammar will produce strings that the PDA accepts. That's kind of what we're doing. Now, that's kind of, that's the motivating definition. Sorry, let me talk about the two cases again. As you compute from P to Q, things are pushed and popped to the stack, and it's kind of complicated, right? But there are two cases. The first case is of this form. The stack is emptied at some point, let's say R, right? If the stack is emptied at some point R, we want to be able to simulate this in our productions, right? We want the grammar to be able to simulate the PDA in this way. So conjecture for me, what kind of productions should our grammar have?
It should be like the split thing, right? Like if you go from the non-terminal V, you can go to like two separate states like P and Q, right? Two non-terminals, P and Q.
Yeah, basically. So let's say one way we could go from PQ is in a computation. And again, there's multiple computations, right? There's multiple non-deterministic computations. But let's say one computation for P to Q has, at a state R, an empty stack, right? So the computation grows and then shrinks from P to R, and then at specifically the instance R, the stack is empty, right? What we can say is if there is a string that brings you from P to Q, then this is the concatenation of two strings, one that brings you from P to R and one that brings you from R to Q, right? Let's take a second to think about that. Do we believe that? Okay. Anyone disagree? That works. We'll prove it works, but are we motivated? Okay. Now, case 2 is that the stack is never empty. Something like this, right? Let's say from state P to R, in a computation from P to Q, let's say that we're looking at the computation from P to Q that the stack is never emptied at some intermediary step, okay? We also can say something, because if the stack is emptied at some intermediary step, we can't say that about here. But here we can say that the first symbol pushed is also the last popped. So when you go here, you're going to add, let's say, some U to the stack, and then when you go here, you're going to pop some U from the stack, right? Not only is it the same symbol, but it's literally been in the stack the whole time, right? It's not been ever removed from the stack. So we know that U is in the stack the entire computation, right? So what we're going to do is, we know such a structure must exist in our PDA then. We have some state P. Let's say we read an A, and then we push the U. No, it's pop, sorry. We pop nothing, and we push this U. And we're at some state, let's say R. And then some things happen from R, and we go to some state S. But then finally from S, we pop the U. By reading a Z, pop the U, and push nothing, right? Now, again, we're considering a computation that goes from P to Q, empty stack to empty stack. So this U pushed, some stuff happens, and then this U is popped, right? And meanwhile, there's an A that's produced, that's read on the input here, and let's say a Z that's read on the input here, right? What kind of production should I add to my grammar to simulate this? This is a tough question as well, and it's basically the crux of the proof.
You add a terminal. APQ goes to U append.
It's a little tricky, but
APR, ARS, ASQ?
almost. The APR, ARS, let's suppose that we can assume that we're not in this case at all. Now in practice, this case will delegate to this case recursively, eventually. But let's suppose we're in this case, right? You said ARS, right? Why? The computation, what is ARS supposed to produce? The strings produced by this non-terminal are supposed to be strings that bring the PDA from R to S, but with an empty stack. So you start here with an empty stack and you end here with an empty stack. But this computation doesn't go from R to S with an empty stack to empty stack. It goes from R to S with just a U in the stack, and it ends on the state with just a U in the stack. But I claim that those computations are identical. If you can push a U, do a computation which never empties, and then pop the U, that computation is almost the same as just going from, if you go from R to S, just U in the stack to just U in the stack, you can go R to S, empty stack to empty stack. Because there's this element of the stack that's never touched. It's as if your array was pretending to be one indexed instead of an array indexed, right? There's just this thing there, you're ignoring it. It's never looked at. Conditioned upon the fact that the stack is never empty, right? So what should my production be here then? This is not complete. So this is another trick thing. U's go on the stack. A's and Z's are going to go in the input. And we want to produce strings that the PDA would take as input. Yes?
A
think you were about to say A, capital A, R, S, Z?
Done. Yeah. Why? Read the A, do some stuff which is going to produce some string that goes here, and then Z is going to be at the end, right? Now, we need a base case. What's our last kind of thing? We're missing a base case, turns out. I don't know if anyone would get this, but let's see.
You mean to get out of ARS, right?
Well, this delegates to this case, and this case may delegate to this case, and so on, right? So we need, recursively, we have non-terminals pointing at each other. We need something to like, by the way, you cannot have a grammar only with productions. If you have a grammar, there must exist some productions that have no non-terminals on the right-hand side. Otherwise, things are just gonna get looped, right? So you need some kind of exit condition, and I can just tell you guys, actually, let's try that. What should APP go to for all P? Yeah.
Empty string?
Why? You're right, but why?
I have no idea.
The definition is like, we're looking for strings that bring, APQ should produce a string when that string will bring the PDA from P to Q, empty stack to empty stack. But if we're concerned with strings that go from P to P, empty stack to empty stack, some of those strings could be on wild loops, crazy detours or whatever, but certainly the empty string always brings P to P, empty stack to empty stack, right? So that's one way to think of it. And we have our constructed grammar. So here's what we'll do. We say for P comma Q in Q, we're gonna define our grammar. I'll define it formally. Fine. Let's suppose we have a PDA that looks like Q, sigma, gamma, delta, and F. We give a CFG, non-terminals, terminals, productions, and the start state as follows. For all P comma Q in Q, add APQ to the non-terminals. For all P comma Q comma R in Q, add PQ goes to APR, ARQ to the productions. For P comma Q comma R comma S in Q, A comma Z are in our input alphabet, and U is in our stack alphabet. Add APQ goes to lowercase a, capital ARS Z, only when PDA has that structure, P, R, read an A, pop nothing, push a U, read an S, at state S, read a Z, pop the U, push nothing, and go to state Q, right? Okay, okay. And then set S to be A0F, right? Am I missing anything? Okay, that's it. Do you have any questions on this construction? And you should. You might. There's something a little off about it.
It seems even, like you always have the A and the Z, so it feels like it only forms equivalent strings.
Oh, sorry. A and Z are allowed to be the empty string as
Okay,
well,
never
right?
mind then.
Sorry. That's a good call. I guess one of the things is like, why do I only have to add this production when I see this structure, but then I add this production for every possible pairs of states, right? Triples of states. What if there is no computation from P to Q that goes through every R, right? I still add this production. Turns out it doesn't matter. by the property, we'll prove that this is kind of like over describing how it works, and that's okay. It just makes a simpler description of the grammar that we're using that simulates the PDA, right? And then this is, we add it only when this structure exists in the PDA. So we add this production only when we see this kind of transitions exist in the PDA, right? A and Z are allowed to be the empty string as well. Questions so far on this construction? Now we need to prove the correctness. So here's what we'll prove. APQ, here's the main theorem of today, right? APQ produces in 0 or more productions a string X if and only if X brings the PDA from P empty stack to Q empty stack. And this is the notation I'll use, okay? This non-terminal produces a string X if and only if that string X brings the PDA from a state P empty stack to Q with an empty stack. And this is kind of the way we'll write this, right? Now, this is an if and only if, so we need to prove both ways. This is going to be kind of the difficult challenge for today. Questions on what we're proving before we do so? Unlike the other proofs we've done where the simulation is like, oh yeah, I could do that. That's like, when we convert the CFG to a PDA, the example was pretty illustrative because you're like, obviously the computation of this PDA simulates the CFG correctly. But here we're talking about a CFG simulating a PDA. Yeah, so it's not obvious that the CFG is correct. And in fact, like, the construction is so complicated here, these rules, I don't even think I could really give you a good example. And you couldn't look at the example and be like, yeah, that definitely simulates the PDA. So what we have to do is simply prove the correctness of such a thing. Our hand is, you know, it's what we're dealt with. So of course, how do we prove an if and only if?
Prove the if then both ways, so
Yeah.
if
Exactly, yeah. So we need to now break it up into two ways. We're gonna prove the forward way first. We prove that if APQ produces some string X, and this means in 0 or more productions, it produces a string X, then X brings the PDA from the state P empty stack to the state Q empty stack, okay? Now how are we gonna prove that?
induction.
Yeah, we're gonna do induction. How are we we proceed, in fact, strong induction, we proceed by strong induction on what? This is a tough one. This is a tough proof in general, by the way.
Number of transitions.
Close. I'll just tell you, we'll do the first one, I think, and then I'll ask questions about the second one. On the number of productions. Okay. So the number of productions that APQ produces X in, right? We get to assume this, and we want to show this. So we'll proceed by induction on the number of productions it takes to do this, right? Base case, APQ produces X in one production. Okay? Now, notice that what possible strings can be produced in one production? You have exactly one production you're allowed to use. Which strings can be produced?
Strings of length 0 to 2.
Sure. Notice though, like, all these rules have non-terminals on the right-hand side. So if you apply a production, you have a working string. You want a string. So a working string without a non-terminal in it.
Only the OT.
Yes. The only production that has no non-terminal is this one. APP goes to the empty string is the only production then. And empty string does bring P with an empty stack to P with an empty stack. Done, right? Base case is done. Now assume our strong induction hypothesis that if APQ produces a string X in less than or equal to K productions, then X brings P empty stack to Q empty stack. If it takes less than K productions. Suppose APQ produces X in K plus 1 productions. So assume it works for all productions of at most K. We want to consider a production that takes K plus 1 productions, right? We want to prove here what? That X brings P to Q empty stack to empty stack, okay? So if APQ produces X in K plus 1 productions, we have two cases. Case 1, first production is the first kind. APQ produces in a single step APR ARQ, which produces in several steps some string X, right? So in the first case, the first production is of the first kind, right? With APR producing some string, let's say Y, no, let's say U, no, let's not do, let's do V, and then ARQ produces some string, let's say W, right? What do you know if APR produces a string V and ARQ produces a string W?
X is equal to VW.
That is true. We'll bring that in at the end though. That'll be the concluding hitter. But what do we know if these two things are true? That is true though. I don't think anyone's gonna get it. I asked knowing, I don't think anyone's gonna get it, but let's see. This is K plus 1 productions. So this is at most K productions. So by our strong inductive hypothesis, we can say that V brings the PDA from P empty stack to R empty stack, and W brings the PDA from R empty stack to Q empty stack. So VW brings the PDA from P empty stack to Q empty stack. And APQ produces in a single step APR ARQ, which produces in 0 or more steps some VW, which produces, which is just equal to X. So X brings the PDA from P empty stack to Q empty stack. Done. With case 1. Case 2. Questions on that case before we continue? Okay. Case 2, the first production is of the form APQ produces, let's say A, ARS, Z. Right? Which let's produce in 0 or more steps some string, let's say AYZ. With ARS produces a string Y in, we don't know how many productions, but definitely less than K. So by our strong inductive hypothesis, we know what about Y?
produces ARS?
ARS is produced.
No, ARS produced by in.
Correct. That is the premise of the induction hypothesis. But if that's true, we know that in fact that it takes the PDA from state to state by induction. So by the strong induction hypothesis, we know that Y brings the PDA from R empty stack to S empty stack. Right? So would you agree? So then Y can also bring the PDA from R just U to S just U, right? If the string can bring the PDA from R to S, empty stack to empty stack, the string can bring the PDA R just U in the stack to S just U in the stack. But we add production. APQ goes to ARSZ when we have this form in the PDA. Read an A, pop nothing, push a U. Read a Z, pop the U, push nothing. From P to R, S to Q, right? So, AYZ brings the PDA from P empty stack to Q empty stack. And AYZ is equal to X. Done. So some string X, this string X brings the PDA from state P empty stack to state Q empty stack because a string Y exists to bring the PDA from state R empty stack to state S empty stack, and that same string will bring the PDA from R just U in the stack to S just U in the stack. Then we see that this computation exists where we push the U and then we pop the U. So definitely AYZ goes from P empty stack to Q empty stack. Done. Questions on this induction proof with two cases? Yes.
The arrow with the star on top of it?
Yes, sorry. That means 0 or more productions. So like, not an implication, but like, you apply a sequence of rules and then you have something with no non-terminals in it, right? Sorry about that, I should have said that at the beginning. Questions? Okay, are we done?
Yeah.
Why not?
We have to prove it. We have to prove the reverse sample.
We gotta do the other direction.
The reverse is similar, right? You just have to revert everything in the middle.
Oh, you would think so. That's my favorite part. It's not simply, it is simply, okay, so conceptually identical. Proof-wise, not the same. But conceptually the proof is the same. But written is not the same. We want to prove this direction, which is that if X is a string that brings the PDA from some state P empty stack to Q empty stack, then that implies that APQ must produce the string X in 0 or more productions, right? If the string brings the PDA here to there, then the non-terminal produces the string as we want. How should we proceed? We're going to do induction again. We proceed by strong induction on what? This is a tough one. What do we induct upon?
The depth of your stack.
Not necessarily. I think something like that could work in a very complicated sense. Something related to that.
Number of transitions?
Almost. Basically, I think you guys are almost saying the same thing. It's related to that in both sense. The number of transitions in what, necessarily? Like in the...
From P to Q?
Yeah, so it's going to be the number of steps of the computation. So as the string x goes from P to Q, it takes a sequence of steps. Some of those may be epsilons, whatever, but we count those. So we induct upon the number of computation steps that the PDA must take, right? Base case, what's our base case? What's the smallest number of computation steps you can have?
0?
Yes. The PDA takes 0 steps. Notice the difference between these two proofs. That has a base case of 1 because you must apply at least one production. If you have no productions, you're just with a non-terminal, start non-terminal. Here you can start and end with a single thing, right? If you have consider a PDA where it has 0 time. It has no time, it can't take any steps. No time to read input. So, we know that X must just be the empty string. It can't read any input, right? No time to change states. So we know that the state P is equal to Q, right? So, the empty string brings P empty stack to P empty stack is true, and we have production APP produces the empty string. So we see that we've proven the theorem in the base case, right? Our strong induction hypothesis is going to be if X brings the PDA from some state P empty stack to Q empty stack, then in specifically less than or equal to some K steps, then APQ produces that string X. Right? Let X go from P empty stack to Q empty stack in K plus 1 productions. Excuse me, K plus 1 steps. Right. So we're inducting upon the number of steps of the computation of the PDA. Suppose we have a computation X here that goes in K plus 1 steps, right? We, again, have two cases. Case 1. In the computation, the stack is emptied at some point. Say state R. Right. Then we can say X is equal to, let's say, VW, where V brings P empty stack to R empty stack, and W brings R empty stack to some Q empty stack. Both of these in less than or equal to K steps, right? So by our strong inductive hypothesis, we know then that APR must produce this string V, and ARQ must produce this string W. And notice we have production APQ produces APR, ARQ. So APQ produces, in a single step, some APR, ARQ, and then a sequence of steps, these will produce V with W, which we know is just equal to X. So, APQ produces a string in the string X in 0 or more cases. So the theorem is proven in case 1 here, right? Again, assume X brings P to Q, empty stack to empty stack. We prove that APQ must produce, the non-terminal must produce this string X. Questions on this case 1? We're almost done. We have now a second case to go. Case 2. The stack, let X bring P empty stack to Q empty stack, and the stack is never emptied at some intermediary point, right? Notice then that the first pushed is the last popped. So, AX is equal to some AYZ, where A, Z are symbols are possibly the empty string, and Y is a string to go from some state R with just U in the stack to some S with just U in the stack. Where we have the form that we go from P to some, let's say, R, and then we go from some S to some, let's say, Q by, we read the A, we pop nothing, and we push the U, and then we go from S to Q by reading the Z, popping the U, and pushing nothing, right? And Y is the string that takes us for some U and for some R and some S. We know that if X goes from P to Q, empty stack to empty stack, and the stack is never emptied, such a structure must exist where the first pushed is the last popped, and that U is just, call it some string here that goes in between there. But if Y is a string that brings the PDA from R with just U in the stack to S with just U in the stack, then and the stack is never emptied, we also know that Y can do this. Y brings the PDA from R with an empty stack to S with an empty stack. And not only does it do so, it does so in less than or equal to k steps. So by our strong induction hypothesis, we know that A R S must produce in 0 or more steps this string Y. Notice we added production APQ produces ARSZ exactly when that thing occurs. So APQ produces in a single step ARSZ, which produces in a sequence of steps some AYZ, which is just equal to X. So APQ produces X. Case 2, done. We have proven that if X brings P from the PDA from state P with an empty stack to state Q with an empty stack, then APQ must produce X. We've proven it in both cases. Okay? And we have now proven the if and only if, so we can suffice to say that every language that has a PDA to decide it also has a context-free grammar to produce it. QED. Let's take a step back. Any questions on this proof? Any questions on the intermediary details? How important is it that you know this proof? You need to have like the ontological humility to know why we don't do these proofs all the time, but you got to see one to know why we're missing out, what we're missing out on, right? This was a difficult proof. I would even say this is the hardest proof in the class. I think other material we'll do is conceptually more advanced, but this is like really tough. It's very, what did we do? We were trying to show a double set containment. We showed one way this is a double set containment just by an example, right? We showed every CFG has a PDA. That was easy. We tried to show just the other way of the double set containment. Every PDA has a CFG. That was very difficult. And what we had to do is prove an if and only if. The if and only if we proved, again, was that APQ produced some string X. If and only if X brings P empty stack to Q empty stack. And then to prove the if and only if, we had to prove one way and then the other. And then to prove each of those, we had to do a strong inductive proof with two cases. So we're several layers deep now, and we're rewinding to get back to the big picture. And we finally have proven, by proving this if and only if, we've proven one direction to set double set containment. Now technically we were supposed to do the other way, right? But we just kind of did an example to show that every CFG has a PDA. You believe me, that one works more than maybe you believe this one works, honestly. Because the construction does not illustrate for you necessarily how that computation proceeds. But because the proof is correct, you probably should be convinced that it does work, right? And you could do it in theory. Now, would I recommend that you convert a PDA to a CFG using this method, where you have the APQ and all such things? Definitely not. It's more of the fact that it works at all. And this, for example, you know when we converted an NFA to a DFA, the point there was not that we have an algorithm that converts NFAs to DFAs. Don't really care about that. It's about the power. It's about the fact that we can prove with certainty that the NFAs are not strictly stronger than DFAs. Same thing here. It's not about actually converting and giving an example, give it a PDA, convert it to a CFG, whatever. No one really cares. It's about the fact that that we know that these two are equivalent. Now in the future, whenever you say, okay, well let L be a language which is context-free, you know you can say then that there exists a PDA for it as easily as you could say that there exists a CFG for it. And this allows you to do both easily, right? Questions on this proof? Yeah, context-free grammar is very difficult. Again, notice in the construction, the PDA has to read left to right, but the grammar simulates this again by going inside out. So it still does it in a very grammar-like way, even though the PDA computes in a very computation-focused way. It ends up being, it's very surprising, I think, that these are identical. That's a very interesting thing. Questions? All right, I'll see you guys on Wednesday.